Hey, this is hacking a treat tossing dog camera with Somerset Recon. A little bit about us. We're Somerset Recon. We do security analysis and research. So on the analysis side, that looks like information security assessments and penetration testing. We cover everything from advanced hardware exploitation all the way to modern web applications and everything in between. So you can imagine the full IoT stack, from hardware and software reverse engineering to network and cloud communication and infrastructure to mobile and web applications. We have a small, tight-knit team that have specialties in all of those areas, and we work really well together on assessment. The other part of our time consists of research. So when there's a new device or technology that comes out that's of interest to us, we put some time on the calendar and we research the device to whatever extent that looks like. And it could also be service. It can be a cloud infrastructure, software, whatever. If it's some new flashy thing, we always love looking at the security. Also, we offer trainings too in various areas, such as RFID, software-defined radio, or lockpicking. A little bit about me. My name is Kenneth Nierenhausen. I've been working at Somerset for a while now. Been doing security research and analysis. I do full stack IoT, security research, and exploitation. So everything from the hardware up to the browser, mobile applications, communication, network infrastructure, all of it. But my main focus is hardware security and reverse engineering. So I focus a lot on the low-level aspects, as well as reversing firmware and those kind of things. My side time, the copious amounts of it are filled with side channel analysis research. So if that looks like power analysis or glitching or things of that aspect, we have a lot of fun as well. But we are a team, and this was a team effort for this research project. So I absolutely want to mention Jared French. He took point on this one. The treat tossing dog camera was his baby. He is a expert network exploitation security analyst and researcher, and he's super awesome at ARM exploitation, and he did a ton for this. So it was really a pleasure to work with him. Also, Nori, Marcus, Morgan, and Danny, thank you very much for all the pieces and parts that you contributed, whether it was review or just positive words. It was really nice to work with everyone on this. So credit where credit is due for sure. The device we looked at for this talk was the Furbo, or I should say is. The Furbo is the treat tossing dog camera. This is an image from their website. You can see from their promotional material that it has a mic and speaker, a 160-degree HD camera with night vision, a barking sensor. It has a treat tosser and also a status LED. So this device is intended to sit in your house, monitor your pet, and allows you to toss treats to your dog or your cat, I suppose, if they're being particularly good, I suppose. They got popular in Indiegogo in 2016. They went public, and then they soon became an Amazon #1 bestseller. So they are doing quite well. The parent company is called TomoFun, and we'll talk a little bit about them later when we get to disclosure. So some of the features, as I mentioned, the Furbo device, it does video monitoring, so it'll monitor your dog when you're away, or your animal when you're away. You can toss them treats by tapping on the mobile device, and you can shoot off treats. And then there are various alerts that come with the Furbo as well. So it will process the video stream, and it will look for dogs, or it'll alert you if there are dogs barking, or if there is a fire alarm detected. So that's really cool. There's also a subscription you can purchase with the Furbo that will provide additional alerts for your dog that include seizures, and if there's home intruders, I think are on there as well. And they're working on one for detecting if the dog throws up, things like that. So it's pretty cool. The architecture of the Furbo and associated devices, aka the mobile app, are an Amazon IoT device. So Amazon AWS has a service called Amazon AWS IoT, and what it provides is essentially infrastructure that you can put in place on a application as a user, on backend server hosting, and then on the IoT device itself. So what this provides is essentially a template that you can put together to really easily create IoT devices, as well as the web or mobile application that the user is going to connect the IoT device with. So in terms of the Furbo, how this works is the user is a smartphone. So when you first get your Furbo device, it'll prompt you to download the Furbo app. So you'll do that. You'll create an account with Furbo, and what that does is it'll register your account with the AWS backend. So the AWS IoT device will then communicate to your mobile client. Your mobile phone will then reach out locally to the Furbo once it's powered up via Bluetooth Low Energy. So that connection exists locally so that your mobile phone can pass off Wi-Fi credentials to the Furbo device. So now the Furbo has your Wi-Fi credentials, so then it can connect to the internet and perform its AWS registration, which goes to the back end, so that your device now gets registered with your Furbo account. So once this process is complete, it allows communication between the Furbo device and the mobile device directly through the AWS backend. So that's kind of the data flow of the Furbo when you're first setting it up. So now your Furbo is connected to the internet, right? We wanted to see what was going on there, kind of look for some vulnerabilities or see if there was anything funky. So we did a simple nmap scan, and we noticed that port 554 was open. Port 554 is typically used for RTSP traffic. RTSP is real-time streaming protocol, which is just a protocol that's utilized in a lot of video and audio streaming. So as you can see from the nmap scan, there wasn't really anything else open. So we looked at the RTSP server or service to see what was going on. Right away, we got a crash. So we were pretty happy. We were like, oh yeah, this is gonna be fun. We're on to something. What we found was when we connect directly to the RTSP service via VLC, we get prompted with digest authentication. So what that means is we'll be asked for a username or password. Username and password. We're prompted for that. We have to enter those credentials, and then they get sent back to the server where we'll verify if you're allowed to access that stream. Good for Furbo, they set that up. However, in the RTSP authentication header, they introduced a parsing issue that crashes the service. So how did we crash the service? Well, we manually fuzzed, and the first thing we wanted to test right away was, I don't know, maybe there's a simple buffer overflow. So we set the username to be 500 A's, as we can see from this chunk right here. So the username we set to 500 A's, sent it off, and we got a crash. That caught our attention. We were like, oh yeah, okay, like we got an actual crash here. This is good. We're buffer overflowing something. But we needed to prove it. We needed to figure out what was going on. So it was time to get shell access. To get shell access, we had to start the process of hardware reversing, doing the teardown and analysis of the Furbo device to figure out how we could get any sort of shell on this device physically. Since there were no other network services running, it was our next option. The hardware consists of 3 major PCBs. There's also a minor LED PCB, which we don't need to go into. It just has the LEDs on it. But this is the back PCB, aptly named. It handles the power, so it just has a USB connector, micro connector. It has a reset switch, which can be utilized to reset the Furbo or factory reset it if held down. And then you can see that cable on the left-hand side, that connects to the other PCB components. And then bonus, there's a couple non-pops on here. There's another reset button, which is tied to the exact same thing, as well as the USB connector on the right-hand side that has the D+ and D- USB pins broken out. I assume that these non-pop boards are used for communication of the Furbo device with pogo pins in the factory, but that being said, they weren't super interesting. We didn't need to explore further there. So the power on this guy runs to the central PCB, which we have coined the muscle. So this is the chip that kind of does all the heavy lifting in terms of actual lifting, the physical components. It controls things like the treat tossing motor, the actuator that measures if there's a treat there. It has the LED controller. It also does voltage regulation. And it handles all this utilizing the PIC 16F57. So we can see right in the middle central area here, this is the PIC chip. There's a non-pop header that you can communicate with the PIC chip. There's a couple other non-pop elements and test points that have data flowing through them. But it's all kind of standard communication, I2C, SPI, stuff like that. Nothing particularly interesting in terms of getting root access on the device. So then we found this device, this PCB, which is directly behind the camera. So actually the back side of this board, right behind this is the camera. But this board, when we pulled it off, we found that it has this Ambarella chip on it. Ambarella created the system on chip. It's called the S2LM. It's an ARM Cortex A9. So it's a full system on chip. It's not just an MCU like the PIC on the other board. We also have the flash sitting right next to it. There's a bunch of test points broken out that you can see. Underneath this heavy shielding, there's some Wi-Fi and Bluetooth components. There are some other connectors that went to IR sensors and the barking sensor and things like that. So we knew right away when we saw this guy that it was like, okay, yeah, this is the brains. This is going to have some good stuff. We're going to take some time to actively reverse this and find out what's on it. And after copious amounts of probing this board and many broken probes, we found that there's a serial UART port on these two pins right here. So there's our TX and RX connection to the Ambarella system on chip. So we hooked it up. We soldered some wires directly to those points, and we hooked it up to an FTDI, which just transmits serial UART to USB, which allows our machines to be able to view what's on those serial UART lines. Now, in the Ambarella case, that's going to be their whole boot log sequence. So we get to the login prompt, but we don't have a password. So one thing that we did was we just cleaned it all up because we knew that this was going to be a major part. This was going to be like a big component of what we wanted to do, was accessing the Ambarella boot logs via the FTDI and then seeing what was going on under the covers. So we made a compressed version. This is the compressed version of the Furbo. You can see it has the major components on it, the mains board. It has the back PCB. The other components are underneath. Here's the LED PCB as mentioned. And then as you can see, we have connected an FTDI here. It's a simple 3.3 volt FTDI with TX and RX and ground hooked up. And then we have our connector here, which goes off to our laptop. And from there, we can see our boot logs. So here's the Furbo boot logs. We have some hardware initialization. Bootloader starts running. And you can see it jumps to the Linux kernel and system D. Typical system D output, you can see it setting up some of the file system components. It's looking at the flash, it's partitioning. And then we're going to get hit with the Ambarella login prompt. So the Ambarella login prompt, how do we get by it? Well, we saw in the boot logs that there was bootloader. It's amboot, it turns out. Amboot is Ambarella's bootloader. It's very similar to U-boot, if you guys are familiar with that. U-boot is one of the most common bootloaders used in embedded devices, and honestly, just devices in general. It loads the kernel, it loads the root file system, it loads any other partitions that are saved in the NAND. Amboot does the same. So it has typical commands and environment variables that you can set once you're in the Ambarella bootloader prompt, as we can see here. So how do you access the prompt? It's in U-boot, there's various ways. You can hit escape, sometimes Control-C, Control-Enter. But in the Furbo's case, It was just holding enter while the Furbo is boot up. Um, so now that we're in the bootloader, how do we get root access, right? Like we are in the amboot bootloader. There's got to be a way that we can get a root shell on this device and modify access, whether that's enabling SSH or that's adding a user. There's got to be a way to do this. So there is. We noticed in the boot logs initially that the kernel command line arguments get thrown by, and so we copied those. We looked at them and we noticed that it had the traditional init equals Linux RC, which is how most devices will, when they first run, that's the first thing the kernel will do, is it'll run that. So what we did, which is really simple, was modify the init parameter to point to bin.sh. So what this does in the Umbrella bootloader is when the kernel command line arguments get passed to the boot parameter, or sorry, the boot command in amboot, it'll run bin.sh as soon as the kernel starts, as soon as we're like ready to go. So what that looks like is here. So we're holding enter, we run the Furbo, we get put into the amboot prompt, we put in our init equals bin.sh, and boom, it drops into an initram fs root shell. You can see our ID there is 0. So we did it. We got root shell on the Furbo. We were super stoked. It was a great moment. And it meant now it was time to tie back the original crash that we had seen in the RTSP service with this new root access that we have on the Furbo device. So we can answer the question, why does the RTSP service crash? What exactly is going on there? We were perplexed. As you can see, our 7th member at Somerset was clearly as complex as we are. So we started looking into it. Now that we had root access on the Furbo device, we reversed a little bit of the software to figure out exactly what was going on. Turns out there's this service run by systemd called Apps Launcher. Apps Launcher is in charge of launching all the services that run on the Furbo device. There's several, as you can imagine, that are there for monitoring the sensors or displaying the video or handling the treats and things like that. But one of the ones that we were most interested in is the RTSP_SVC. So that file, that executable, is the RTSP server that's running on the Furbo device. So that's the thing that we're seeing crash. So what we see when we run our exploit, we manually ran Apps Launcher on the command line so we could see the log output. What we see here is when we run our exploit against the RTSP_SVC executable, we get 2 seg faults before the device resets. So we have 2 seg faults happening, and the really exciting part is, if you remember, we filled the original request with 500 A's. Is we see the address in the seg fault is set to 414.14140, which we're just like, okay, yeah. We're getting a buffer overflow. This is going to be really fun. So then we started the process of tooling. How can we start taking control? What can we do with this buffer overflow? Really fun. Oh, I love this stuff. So we put GDB server on the Furbo device so that we could do some dynamic testing and see exactly what was in memory when things were crashing. So we put on a static compiled version of it. And then on our local host side, we set up GDB multi-arch and the Jeff plugin, which nicely presents the GDB output in just a little bit more understandable of a format. So here we can see some of the Jeff output. You'll notice the registers are completely blown away by A's, as well as the stack pointer and the program counter. A bunch of other memory has also been filled with A's. So we're getting these 2 seg faults. Memory's totally filled with A's. But why? What's going on? What's causing? What part is causing this? Well, GDB has this really awesome little feature. If you can see in gray, this pointer right here figures out the function that it's pointed to, and it's called parse authentication header. So we know that the function that's failing, that's causing this seg fault, is called parse authentication header. So we did some stringsing and reversing to figure out where this guy was. And it turns out it lives in a file called libamprotocol-rtsp.so.1. So we popped that file into Ghidra. We started reversing to see what exactly was happening under the covers so we could figure out how we could exploit this thing. So this is the Ghidra output. It didn't quite nail it. You tried Ghidra? It's funny, IDA actually failed at parsing this properly too. But you'll notice it's missing a parameter after the parameter. There should be value, which also gets passed to scanf. But minus that nuance, the important piece is that, hey, libam protocol RTSP is calling parse authentication header, which calls scanf. Scanf is taking user input parameter and copying it into requester and not checking lengths, which is a no-no. So this is our buffer overflow that we're seeing. So we were stoked. So it was like, oh, okay, we have an scanf buffer overflow. It's like time to start crafting an exploit. So that was our next step. So what do we need to do to craft the exploit? Like when you find a buffer overflow in the wild, like you need to figure out a few things, right? So the things that we need to figure out was what was going on internally in the Furbo in terms of memory. So there were a couple limitations. ASLR is running on the Furbo device by default. So when the Furbo starts up and when processes start, the address space is randomized. So you're never going to know exactly where, for instance, libc lives. That's going to vary every time processes up and start. The RTSP service itself we looked at, and we found that it had NX enabled. So that means we weren't going to be able to execute in the stack space. So NX stops you from being able to execute in stack space. So we weren't going to be throwing bytecode in and just executing there. That wasn't going to be a possible path for this exploit. But what was really cool was RTSP was not compiled with PIE. So that means we could theoretically ROP in the RTSP text section. And we were like, oh yeah, this is going to be the path forward, until we looked at the proc maps and saw that the RTSP SVC actually starts with null bytes. So you'll notice the address location starts with null bytes. Now, normally this wouldn't be an issue. You can get around this in different ways. But in our case, because our crash is in scanf, scanf is going to stop processing the second it sees null bytes. It's going to be like, oh, okay, your string's over. We're done. So if we provided a exploit payload that contained null bytes to ROP internally on the RTSP SVC, it wouldn't have worked. So that means we had to look elsewhere. So that's just another limitation that we're not going to be able to directly ROP in the RTSP service PIE because PIE. Sorry, that was totally backwards. We're not going to be able to ROP in the RTSP service file because of the null bytes, even though PIE is enabled. But it's not all bad. We do have a couple benefits. So like what's working for us when we talk about crafting this exploit? We do have the watchdog script that's running on the RTSP service. So when we crash, it'll seg fault twice and then crash. And then the watchdog will reset. So it seg faults twice, resets. Seg faults twice, resets. Which is super cool because that means we have a lot of tries we can shoot out to the Furbo and see if things are working while we're triaging. The other big really cool thing is that it crashes twice. Or I shouldn't say crashes. It seg faults twice. So there are two seg faults. So that gives us two opportunities to potentially introduce these payloads when we talk about ROPing in this section. So those are kind of the pros and cons that we have going for us. So we have this extra ability, but we also have some limitations when it comes to memory. So it's time to dive a little bit deeper. The next thing we looked at was instead of just providing 500 A's in the username, we provided a cyclic pattern. So what the cyclic pattern does is it allows you to start looking at the offsets of where you're going to be inserting values into your payload that you're sending into your buffer overflow. So these cyclic patterns, what they tell us, as you can see from more Jeff output from GDB, is we can see that we have control of these registers, and now we know the offsets at which these registers are going to be located. So instead of sending AE4A, if we want to populate register 4, we'll send it with whatever value or address we want register 4 to point to. Really important to note, too, that with the Jeff output, we saw that the stack pointer gets blown away at offset 168, as well as the program counter at offset 164. So we have full control of the stack pointer, program counter, and all those registers. And if you ever need to generate these cyclic strings, just as a note, there's a lot of tools on GitHub you can find, and then also Metasploit has it built in, and then GDB Jeff has the ability to generate these as well. So now it comes to crafting the exploit. We think about the memory limitations that we have. We cannot ROP internally on RTSP SVC, but we can ROP on libc or something like that. Now ASLR was enabled, so that means accessing libc isn't really straightforward. So for our first POC, we just wanted to prove that we could get RCE on this device, so we disabled ASLR. So we went onto the Furbo device and disabled ASLR to make our lives a little bit easier for finding our ROP gadgets. So now that we had ASLR disabled and we knew the base address of libc, which turned out to be 76D52000, we started looking for some gadgets to be able to place things in the registers we controlled, so that we could get execution. Now, our path on this, we used 2 gadgets with a goal of essentially executing system located in libc. So system requires your R0 parameter to contain the execution payload. So system will call whatever's in your R0. So you can see from our 2 gadgets here, so the first thing I should mention we do is we load the address of system into R8. So in our payload, we put system address into R8, and then our first gadget, what it's going to do is it's going to load R8 into R3, and then it's going to BLX or branch load execute into R4. So you can see we put that ROP gadget at PC. So PC is going to load R8 into R3 and then jump to R4. Not jump, branch. And then we put our payload to execute at the stack pointer, and we found another gadget that moves the stack pointer to R0 and then branch load executes to R3. So what that looks like when we talk about the flow of this exploit is system gets loaded, PC points to system, and then executes R4. R4 will load our payload into R0. So now what we have after this exploit has ran in this overflow is we have system ready to be being pointed by the program counter, and then we have R0 filled with our payload. So we wanted to prove it. We wanted to show that it worked. So we wrote a quick Python POC. We can see the gen payload function here. So we load our various addresses for the ROP gadgets, and then we load our payload here. You can see it's user bin curl shell.sh, and then it executes shell.sh directly with bin bash. So the design of our server, our POC, starts a local Python server. So it creates this local Python server. The exploit itself will then execute on the Furbo. The Furbo will pull shell.sh from this server, and then it will execute shell.sh. So shell.sh, what it does is pretty simple, is it just gets another file on this server called shell.service, and shell.service gets pulled over to Furbo, and then we utilize in the shell.service.sh file, we utilize systemd to enable that service file and start running it. And what that shell.service file does is start a netcat bind shell. So the reason we did all this is because when you execute this POC, when it once the first time, you'll get a persistent shell, which is really, really rad. It's always nice to have that. So here's an example of it running. This is just a quick rundown. So we can see we run our Python exploit up here. We can see it sets the shell.sh and shell service file with some parameters that we want to set. It then starts the Python server. It starts attacking the Furbo. It checks for an open port. It notes the RTSP service is running. And then because ASLR is disabled, we're going to try at this address, which we know is libc. Once it executes, we're going to check again to see if our netcat bind shell is open. And sure enough, it is. We have our ID here of 0. And this is thanks, by the way, to PwnTools interactive shell in Python that it starts running right away into our shell in Furbo. I highly recommend using PwnTools interactive shell. It's really, really cool. So that's really rad. We got a shell. We got RCE on the Furbo. Awesome, right? We're done. No, we're not done. We disabled ASLR. So like, what does that mean, right? Realistically, it's like if we stopped here, it means you would have to go to a Furbo, crack it apart, find the serial lines, tap them, get root access, add your username, like run your exploit, and then it's like we don't want to do that. It's not realistic. We want to be able to enable ASLR so we can attack the Furbo directly. You can just join the network that the Furbo's on, adjacent network access, and you can hit the Furbo and own it. That's what we want to do. So how do we bypass ASLR? How do we get around this? As we mentioned earlier, because PIE is enabled, but the null bytes issue prevents us from ROPing internally, it means we can't ROP in RTSP SVC. And that's a bummer, because if we could, it means we could bypass ASLR really simply, but we can't. We also, as a note, we looked for additional leaks to try and find if we could figure out where the libc address was so that we could really easily do this. And bypass ASLR, but there weren't leaks available. We reversed a few other binaries to see if it was possible, but they were pretty solid. Not saying it's impossible, but we didn't do it. So how did we get around this? Our technique was called, we coined brute forcing ASLR. So what brute forcing ASLR looks like to us is retrying the same address over and over and over again when the RTSP service restarts. Because what that means is when the RTSP service restarts, the libc address is going to be, that'll give us the option to try and run our exploit successfully. So we know the chunk of memory where the libc address is going to exist only has 12 bits changing, which means there's a 1 in 4096 chance that we're going to actually hit the correct libc address. So we hard-coded our POC with 2 libc addresses to be able to see if we could hit that, just guess the libc address when the RTSP service restarts. So how do we choose those addresses? We took a pretty large sample set of libc on the Furbo device after restarting it many times, and we looked at what that space looked like. So you can see here we start at 76C, we end at 76D, and you can see it's pretty evenly distributed. So we just chose 2 addresses within that range, and we have our exploit able to run now. So let's take a look. Here's the running exploit with ASLR enabled. So you can see it's trying to connect. It tries different base addresses over and over and over again because it's just restarting the RTSP service. And on this particular occasion, we hit libc properly, and our ID is 0. We're root. Oh, look at else we have access. Super cool. So sorry, testing. We have fully functioning our RCE POC with ASLR enabled on the Furbo device. Woo! It was rad. We were done. We were finished. We were stoked. It was over. It was complete. It was a journey, which is really fun. But we had tested over and over again to see how this thing was running, kind of see what type of timing we got on our ASLR bypass, and it varied pretty greatly, anywhere from 4 minutes to 4+ hours. And in the worst case, the RTSP service would hang, And if the RTSP service would hang, which you wouldn't notice right away, that would require a hard reset of the Furbo. So those are some of the limitations of this POC, but it still allows you to RCE on adjacent network, which is super, super cool. So we're stoked. So we wanted to look at the internals of the Furbo to see what we could do now that we have RCE on it. These are some of the local Furbo scripts that the TomoFun team wrote. So FB is Furbo. And then here's a few of the things that they wrote. So you can see they wrote FB A Play. If you're familiar with A Play, it just plays audio. So they wrote a wrapper. They also have A Record, which will record audio. They have A Night, which will toggle night vision on the Furbo device. There's also Snap, which will take a picture. And then there is Burning, which does a bunch of burn-in tests that include changing the LED colors and testing that the treat shooter is working properly. Another directory found really interesting was dev ADC. So you'll notice some of the file names in dev ADC are pretty juicy. Things like furbo_ap.info or furbo2_rtsp.password. So those sound really good. Those would be nice to know, right? So we took a look at those files, and sure enough, the AP file has your Wi-Fi credentials. And if you change your Wi-Fi credentials, the backup will actually have your old credentials, so it'll have two network credentials on there. And then the RTSP password contains the password for the RTSP stream. So if you wanted to view the video on RTSP, it is protected by username and password. But if you use the buffer overflow RCE and then go into this directory and look at the password, it will allow you to view the RTSP stream. So here we just have a picture of opening VLC and providing the password found in dev_adc furbo rtsp.password. And you can see again, our 7th member is very upset looking outside. Hacked. So we have a demo video of the device running here, of our script running fully, completely with all the bells and whistles. The only thing we did do was disable ASLR. So here we go. Furbo is pwned, LED turns red, shoots treats. So we loaded our script to do all that. And then it pops you into a root shell once it's done. So that's just what we wanted to do. So now we have root access. This is just for demonstration, but you can see we can turn the LEDs blue. You can manually call those Furbo functions. Okay. To toss the treat. You can also change the LED again. So we change it to yellow, or you can change it to purple. There's other colors as well, such as green. I think white's on there too. But you have a root shell. Super rad. Stoked that we got it. So now we talk about disclosure. We had all this. What are we going to do about it? So we actually originally found this POC just over a year ago, or this vulnerability, I should say, and we developed the POC in August of last year. So we had our first working version of this POC in August. That's when we started the disclosure process with TomoFun and the Furbo security team. So we talked with them through mid-August timeframe, and they elevated this issue to Amberella, who they worked with through that timeframe. That's when we applied for our CVE. We reached out again to Furbo to let them know that the CVE was going to be going public. We reached out a few more times in September and October to let them know. We let some time pass. Mostly we got really busy with work, but then we got back to verifying that our POC was still working or not. Maybe they patched it. We hadn't heard back from them, so we bought another Furbo. And when we bought that Furbo, it turns out it was a new model. So the old model, as you can see on the left picture here, is the Furbo 2, and the new model is the Furbo 2.5T. It's like the new Terminator. Um, so just when we thought we were done, and it was finished, and we were like, "Rad, let's go do a talk on this." We're like, "Oh, okay, we got to do some new testing." So we purchased a new Furbo, uh, saw the new revision. We noticed a bunch of hardware changes right off the bat, so that was concerning that our POC might not work. And then we saw when we accessed the thing that the software was different as well. It was running different firmware. Um, so then we ran our POC. We were hoping, we're like, okay, let's do this. Ran the POC. It crashed like normal, but it didn't restart. Ugh. So it turns out on the Furbo 2.5T, they mitigated the issue of the buffer overflow in the RTSP service by disabling the watchdog. So no longer will the RTSP service crash and restart. It will just crash, and you'll have to physically reboot the Furbo to use this exploit. Successfully patched. So we took a closer look at what else we could do on this device because we had it, and we noticed Telnet and HTTP were open on our initial nmap scan. So the RTSP service was there, but so were Telnet and a server on 80 and 443. So we were really curious. We were like, okay, that's going to be fun to investigate. The Telnet stuff, not so much because it uses the password for the Furbo itself. That's calculated, and we weren't quite interested in looking at that. But the HTTP server that we looked at used digest authentication. So we were curious. We're like, okay, what's going on with this? Back to the UART shell. So once we got access to the UART shell on the Furbo 2.5T, we poked around a little bit looking at what this server was doing. And it turns out it's a light TPD server, very frequently called Lighty. It's an embedded HTTP server that's used in a lot of IoT devices that are passed around. It's pretty solid, but in this case, it was using digest authentication. So we looked for the digest file, and we found in etc light tpd /webpass.txt contains the digest, which had the username and password as well as the hash. So we cracked the hash, got the username and password, and then also noticed that the realms were different. So in that same directory, in the etc light tpd directory, etc light tpd directory, lighttpd.conf contained the realm information. So when we initially submitted this request, it failed. So we cracked it. We knew what the username and password was, but it was failing. So we were like, what's going on? So it turned out it was a realm mismatch. In this authentication, if you don't have the proper realm, it doesn't matter if you have the username and password correct. You have to have the realm correct. So how do we change the realm? Well, it turns out you can modify the realm on the response from the HTTP from that server. So this is a little bit wonky, but essentially what happens is you send it username and password, you get a response back that has a realm, it has a nonce, it has a couple other bits of info that are utilized to calculate the digest authentication. So if you modify that on the response coming back to you and you get the realm correct, then you'll be able to successfully log in. So we spoofed the realm, we calculated the digest authentication header, and the server accepted it. So as you can see in the bottom right picture, we have our login successfully to the Ambrella Smart LDC, which has some lens calculation. It's part of Ambrella's GitHub, but essentially we have access to the Ambrella server now. So what is this Ambrella Smart LDC? We wanted to answer the question of what is it, who cares? So we started reversing the Smart LDC executable to see what was going on. It calls ldc.cgi. So ldc.cgi was our main point of interest. So we popped ldc.cgi into Ghidra and started reversing. Right away we found an S in printf. Okay, the N, we're doing all right. However, they are taking a bunch of parameter values. Okay, we're taking a bunch of parameter values and they're popping it into command. And then you can see in command, they're just calling system on command a little bit lower. So that is a prime candidate for command injection, which is what we did. So we wrote a quick script the same day to do some command injection on that server once we had the authentication calculations correct and the realm proper. And you'll notice, boom, we get popped into a shell. So, hey, they mitigated one and opened another. So we got shell, we ran ID. You'll notice the ID is 0, so they're actually running their server as root, which is always a nice find. So now we have root access by simply executing this command injection. So disclosure, we actually just found this more recently when we were retesting our buffer overflow RCE. So we discovered it in March. We created the POC the same day. Like we mentioned, we reached out already to Ambarella directly through LinkedIn. We found some emails online of some prominent people that we to. And then we also tried to use their web form. It turned out to be broken at the time, but just more recently, last month, it was fixed. We submitted more information there to them. We also reached out to TomoFun. And then we applied for our CVE, and that's in the works right now. And then we're giving a talk on it, which is today, and I should have filled that in. All that being said, we're still looking to get in contact with people at Ambarella or TomoFun. If there's humans you know that work there, we'd love to work with them to patch up these vulnerabilities. So feel free to pass any information our way if you guys have that contact. So why does it matter? What does it all mean? What have we done here? Essentially, we have two exploits here, one buffer overflow RCE and one command injection that allows us to gain access to the Furbo devices when you're on an adjacent network. So what does that let you do? It lets you remotely watch video. So you can pop open that RTSP password file and view the video stream, providing the username and password. You can listen to the microphone. So this is in someone's place. You can start listening to what's going on, whether that's the dog or conversations that people are having. You can play custom audio or sounds, so you can either entertain their dog or freak out the human. You can also shoot all the treats. That's always really fun if you just run the treat toss shell script and pass it, 500, it'll just shoot treats forever. One important thing, a little less silly, is you can steal the Wi-Fi credentials, both of the current network and the past network. That's a big deal, You can connect, you can own the Furbo and you can access the network via the Furbo, but it also has those creds, so then you can directly access that network if you're in that area. And that's no fun because that can establish a foothold. That can be the beginning of a lot of attacks. So kind of the weakest link argument, right? The last thing you can do with the Furbo is brick it. The device costs $100 to $200, so it would be kind of an inconvenience if you did brick the device. RMR star, whatever, no big deal. So the POC is available for the buffer overflow on our GitHub. That's github.com/somerset-recon/furbo-research if you want to access it. You can execute that and you can do the things that we listed. If you want to reach out, feel free to hit contact@somersetrecon.com. We'd love to talk, whatever you're interested in. You can also check out our website. We have our blog post there, and we have contact information and a little bit more about what we do. And thank you very much. That's all I got. I will pass on questions to my future self now. Thank you, future self, wherever you are.